So there is cell, and inside the cell there is glycogen molecule, where glucose molecules are connected with each other by 1,4 glycosidic bonds. And also there is branch that is formed by a glucose that is connected by 1,6 glycosidic bond. And this branch consists of glucose molecules that are connected by 1,4 glycosidic bonds. The breakdown of glycogen occurs in reverse direction to glycogen synthesis. The major enzyme in glycogenolysis is glycogen phosphorylase. This enzyme uses inorganic phosphate and cleaves 1,4 glycosidic bonds. As we see, most of the glucose molecules in glycogen structure are connected exactly by 1,4 glycosidic bonds. And because of that, glycogen phosphorylase is the most important enzyme in glycogenolysis. So glycogen phosphorylase uses inorganic phosphate and cleaves 1,4 glycosidic bond, thereby releasing glucose 1-phosphate molecule. Obviously, with cleavage of one glucose molecule, glycogen becomes one glucose molecule shorter. This systematic cleavage occurs until the 4 glucose molecules will remain on a branch, and these 4 glucose molecules combine, called limit dextrin. So basically, term limit dextrin refers to the 2 to 4 glucose molecules that are remaining on a branch after glycogen phosphorylase has already shortened it. So now the goal is to degrade limit dextrin, and for this purpose we have the branching enzymes, which is logical because in glycogen synthesis we have branching enzyme that creates branches. And actually in glycogenolysis we have 2 debranching enzymes. The first debranching enzyme called 4-alpha-D-glucano transferase. What this enzyme is doing? So to remove the limit dextrin, the first debranching enzyme initially cleaves 3 glucose residues from the branch and transfers them to the last glucose molecule in a glycogen chain. The branching enzyme connects these 3 glucose molecules to a glycogen chain by a 1,4 glycosidic bond. So the net result is that now in the branch we have only 1 glucose residue, and the glycogen chain becomes 3 glucose molecules longer. The second debranching enzyme called alpha-1,6 glucosidase. Alpha-1,6 glucosidase cleaves 1,6 glycosidic bond, thereby removing the last glucose molecule from the branch. As a result, glucose 1-phosphate molecule released, and the branch is completely removed. Now we have a chain of glucose molecules that are connected by 1,4 glycosidic bonds in a linear fashion. So now they can be cleaved by glycogen phosphorylase. Glycogen phosphorylase cleaves 1,4 glycosidic bond. As a result, glucose 1-phosphate molecule is released, and glycogen becomes 1 glucose molecule shorter. And in this fashion, glycogenolysis occurs systematically over and over. So it's a major pathway of glycogen degradation. But the small amount of glycogen is broken down in lysosomes. Lysosomes have an enzyme that is called acid maltase. And the unique feature of this enzyme is that lysosomal acid maltase has both 1,4 and 1,6 glucosidase activity. So it's basically 2 enzymes rolled into one. And the final product of lysosomal glycogen degradation is also glucose 1-phosphate. Lysosomal pathway basically helps the major pathway in tissues with very high amount of glycogen, and its liver tissue and muscle tissue. As we see, glycogenolysis results in massive release of glucose 1-phosphate. So what happens with glucose 1-phosphate? Let's take 2 tissues that have the highest amount of glycogen in the body. It's liver tissue and muscle tissue. Initially, glucose 1-phosphate is converted to glucose 6-phosphate, and glucose 6-phosphate can be metabolized through different pathways. First of all, tissues can use glucose 6-phosphate in glycogenolysis with energy production, so both liver and muscle tissue can use glucose for own needs. But in contrast to muscle tissue, liver tissue can maintain blood glucose level. Recall that glucose with the phosphate group cannot leave the cell. And liver tissue has a specific enzyme called glucose 6-phosphatase that can cleave the phosphate group from glucose. This results in formation of a free glucose molecule that can freely exit into the blood through a GLUT transporter. So because liver can produce free glucose, liver can share glucose with other tissues. And basically liver is the major tissue in our body that is responsible for maintaining of blood glucose level. So muscle tissue do not have glucose 6-phosphatase. So we can imagine muscle tissue as a selfish tissue. Muscle tissue uptake glucose from the blood, stores these glucose molecules in form of glycogen, but muscle tissue can use these glycogen stores just for own needs. In contrast to muscle tissue, liver tissue has glucose 6-phosphatase. And this enzyme permits liver tissue to share glucose molecules with other tissues. So liver is a generous tissue. So as a muscle tissue, liver uptake glucose, store glucose in form of glycogen, and liver also can use glycogen for own needs. But the major difference is that in the time of needs, when glucose level in the blood is low, liver can share its own glycogen reserves for the common good.